0 to 2, integral 0 to pi. Okay, antiderivative of this with respect to r is 1/2 xr squared. Yeah? Antiderivative here, 1/3 r cubed cosine theta plus the same thing, 1/3 r cubed sine theta. Evaluating r equals 0 to r equals 1. And I still have out here d theta dx, right? When we plug in 1 for r, we're going to get some stuff. When we plug in 0 for r, everything goes away. So we should just be at this. 2 integral 0 to 2, integral 0 to pi. What do I get when I plug in? 1? 1/2 x plus 1/3 cosine theta plus 1/3 sine theta d theta dx. Integrate with respect to theta now. Equals 2 integral, oh, I'm integrating only 1 now. 0 to 2, antiderivative of 1/2 x with respect to theta. 1/2 x theta, right? Plus 1/3 sine theta minus 1/3 cosine theta. Evaluated theta equals 0 to pi dx. Almost there. Be a little careful here. 2 integral 0 to 2. All right, let's plug in pi first, right? For theta, we get 1/2 x times pi. All right, sine of pi, 0. Cosine of pi, -1 times -1/3, so plus 1/3. Agreed? When you plug in 0, be careful because not everything goes away. Theta goes 0 here, that's gone. Sine of 0, that's gone. Cosine of 0 is 1, but then minus 1/3, but we're subtracting this one, right? So minus 1/3. So it's going to be plus 1/3, isn't it? So here's where we are. 2 integral 0 to 2 of 1/2. I'm going to write pi x instead of x pi, plus 2/3 dx. And integrate with respect to x. 2, antiderivative here, 1/4 pi x squared plus 2/3 x, evaluated 0 to 2. When I plug in 0, it's all gone, right? When I plug in 2, let's see what I get. 2 squared 4, but then 1/4, so just pi, and then plus, plug in 2 here, 4/3, but then times 2. Oh, wait, sorry, I haven't done that yet. 4/3, like that. And then you can distribute the 2 through 2 pi plus 8/3, which is the same answer you would have got had you done it the other way. But this required a little work. It took me 20 minutes to do it the other way. I think that might have been a little faster. I don't know. Took 10? Okay. So a little more efficient, all right? Questions? So the things that you're going to be looking at when it comes to divergence theorems, first of all, can you use it, right? Like, do you even have the right thing to use it? Then, take a look at the div. Is the div nice? Is it something you really want to mess with? And then look at the solid itself. Can you find appropriate restrictions for your triple integral? If those all look like they lend themselves more to the theorem, then use the theorem. If not, then just do it the traditional way, break it up into separate surfaces, and be done. All right, I have another one. I'm actually moving a lot faster than I thought I was going to go here. we may have time to play, what's that game? Heads down, thumbs up. We'll turn down the lights. Everyone puts their head down, put your thumb up, and then we go, yeah? You want to do that? We haven't played that in a long time, huh? What is it, what?
Heads up, 7 up.
Yeah, heads up, 7 up. I knew it had something to do with 7 up. We'll do that at the end, okay? All right, this, just so you know, this is from 12.9. This is out of the homework. This is number 6. Actually, I did assign this for homework, but I'm going to do number 6. So here's what it says. Here's a vector field, x squared yz, x y squared z, x y z squared. All right, that's your vector field. It's giving you a surface S, which is a box that is the intersection of these planes. Box, which is the intersection of, or I should say this box, not the intersection, is bounded by these planes. The intersection of those would not work. It's bounded by x equals 0, x equals a, y equals 0, y equals b, z equals 0, z equals c. Find the flux. Find the flux through this surface. X equals 0 is the YZ plane. Y equals 0 is the XZ plane. Z equals 0 is the XY plane, right? So you're basically in the first octant. And then X equals A is just a plane that is parallel to the YZ plane. And let's assume A, B, and C are positive here, okay? Just for simplicity's sake, so when I draw it. I should have something like this. Here's the first octant. Here's X, here's Y, here's Z. If X is A, Y is B, and Z is C, then I should get a box that looks like this. Do you all agree with that? Sorry, it's not, I should say rectangular box, right? Rectangular box. It's not a cube. Does that make sense to you? X equals 0 is the back side of this. X equals A is the front side. Y equals 0 is the left side. Y equals B is the right side. Z equals 0 is the bottom. Z equals C is the top. All right, that's our surface, and we want to find the flux. Automatically, we're thinking this is better off as a divergence problem, right? Because that is very simple to figure out what the restrictions on X, Y, and Z are, right? But the div is what we still need to figure out whether or not we want to mess with. So what is the div of F here? So derivative of that with respect to X is 2x yz plus another one of those, right? 2xyz plus 2xyz, which is 6xyz. That seems like something I don't mind integrating. So this should turn into the triple integral over E of 6xyz, so I'm pulling the 6 out, with respect to volume. So we need to be able to come up with our constraints on x, y, and z that will create that solid E, right? And I don't need to convert to polar or cylindrical, right? This is all straight up, this is rectangle. So what are the restrictions on x, y, and z? 0 to A, 0 to B, 0 to C. And so my triple integral over here turns into I'll go 0 to C, 0 to B, 0 to A of x, y, z, d, x, d, y, d, z. I could do that. I could have done that in any order, right? Since these are all separated by multiplication, can I break this into 3 integrals and multiply them together? Yes. Or I could just do it all at one time. I'm going to break it apart. I'm going to have 6 times the integral from 0 to c, and that goes on the z variable, right? Z dz times integral from 0 to b of y dy times integral from 0 to a of x dx. And the 6 does not, you don't get 6's on each one of those, right? It's just 6 one time. Understand what I did? All right, I think if we do one of these integrals, we can see what all of them are going to turn into, right? So what's the antiderivative of z dz? Well, it's 1/2 z squared evaluated 0 to c. So you get 1/2 c squared. That's what I'm going to get for that one. This one should turn out to be 1/2 b squared, and that one should turn out to be 1/2 a squared. And then times 6. So I'm going to have 6 times 1/2 z, not c, c squared, times 1/2 b squared, times 1/2 c squared, which is 3/4 a squared, b squared, c squared. I put it in alphabetical order. That's it. Understand? Any questions? Yes, this last one, thank you, should be an A. Appreciate that. Because my last integral is with respect to x, so that should have been a squared. No question? Nice theorem, huh? I've got another, let's see, how many more do I have here? One, I have one, two more, and then I'm going to show you one last thing, and then we're going to be done, and you can start crying. My 6-year-old daughter broke my heart this morning. Mom had put her hair up in a certain, almost like, what's the Star Wars lady that has the little, almost like Princess Leia buns. They didn't look that ridiculous, but little things like that. And she did that last night. My wife leaves real early to work, so I usually get my daughter up, take her to school. And one of them was messed up, so I tried to fix it. And I took it out of the thing that was holding it, and I could not get it back, and she cried for the rest of the morning about her hair not, I couldn't do anything about it, I don't know what to tell her. And today was supposed to be picture day, and that's why she was so upset. But it turns out that it's next week, so she got to school, and she's really emotional, and when she cries, she's real light complected, and when she cries, she gets real red and puffy in her face, and so she was even more upset that she was upset because she knew she was going to look like all puffy in her picture. So I hope when she got to school and they told her no pictures today that she was finally relieved. But I felt bad.
It's okay.
That's right. I'm trying to get her to understand it's not all candy and fun.
She rocked it one month.
What's that?
She rocked for 1 month.
My neighbor. We switch off taking them to school, and my neighbor, she tried to salvage what she could. It was better than I did. Okay, so here we go. We have a field here. We're asked to find the flux, over the surface. Why am I telling you that story? Oh, because I was saying you can cry. I was like, class, we'll be done. You can cry, and I was thinking about my daughter crying. Okay. Like, what the hell am I telling you that for? Okay, the solid we have here.
Random story time.
Yeah, the surface we have, S, comes from this picture here. Right, we have x is equal to 2, backside x is equal to -1, and this cylinder is y squared plus z squared equals 1. Do y'all kind of see it? I don't really like my x, y, z axes there, but is that okay? All right. So the surface is the entire surface that encloses, so both end caps and then the cylinder around it. So what do you think? Divergence theorem? Yeah, of course. So let's look at the div first. What's div f? 3y, oh, not a vector. 3y squared plus 0 plus 3z squared, right? What's that? Yes? What happened? Did you just like upset everyone? Everyone's like, okay, one by one, they're just leaving that table. I don't know what you guys are doing over here, but all right, this is it. This is our div.
Yep.
All right, I think we're okay integrating that. And you know what makes me feel even better about it? The y squared plus z squared, when I factor a 3 out, is going to lend itself very nicely to the polar conversion or cylindrical coordinates I'm going to go to describe this surface, because I have circles in the yz plane. So everything's looking like perfect here, right, for what I want to do. So this is equal to triple over E div f. I'm going to pull the 3 out. Of what, y squared plus z squared dv. All right, tell me what my conversions are. What are my conversions here? Okay, y equals r cosine theta. Z is r sine theta. And then everything that follows from that, right? The restrictions I will place on theta are what? 0 to 2 pi. So remember, if we're picturing this cylinder, where it intersects the yz plane creates a circle of radius 1, right? Because of this equation. And so I want the whole circle, 0 to 2 pi. I want my radius to go between 0 and 1. And the last variable, which we need a restriction on, x is between -1 and 2. So now this becomes 3 triple. This is actually r squared because of the Pythagorean times r because we did a conversion. So it's really what? R cubed? R cubed. D, does it matter? Order here? No. So r theta x, okay with you? X goes -1 to 1, or 2, sorry. Theta goes 0 to 2 pi. R goes 0 to 1. Dot, dot, dot. Do you want me to dot, dot, dot that? Yes? Okay, 9 pi over 2 is what you will get.